Chapter 17, Drawing on Canvas. Drawing is Deception, M.C. Escher, cited by Bruno Ernst in The Magic Mirror of M.C. Escher. Browsers give us several ways to display graphics. The simplest way is to use styles to position and color regular DOM elements. This can get us quite far, as the game in the previous chapter showed. By adding partially transparent background images to the nodes, we can make them look exactly the way we want. It's even possible to rotate or skew nodes with the transform style. But we'd be using the DOM for something that wasn't originally designed for. Some tasks, such as drawing a line between arbitrary points, are extremely awkward to do with regular HTML elements. There are two alternatives. The first is DOM-based but utilizes scalable vector graphics rather than HTML. Think of SVG as a document markup dialect that focuses on shapes rather than text. You can embed an SVG document directly into an HTML document or include it with an image tag. The second alternative is called a canvas. A canvas is a single DOM element that encapsulates a picture. It provides a programming interface for drawing shapes onto the space taken up by the node. The main difference between a canvas and an SVG picture is that in SVG, the original description of the shapes is preserved so that they can be moved or resized at any time. A canvas, on the other hand, converts the shapes to pixels, colored dots on a raster, as soon as they are drawn and does not remember what these pixels represent. The only way to move a shape on a canvas is to clear the canvas or part of the canvas around the shape and redraw it with the shape in a new position. SVG. This book won't go into SVG in detail, but I'll briefly explain how it works. At the end of the chapter, I'll come back to the trade-offs that you must consider when deciding which drawing mechanism is appropriate for a given application. This is an HTML document with a simple SVG picture in it. The XMLNS attribute changes an element and its children to a different XML namespace. This namespace, identified by a URL, specifies the dialect that we are currently speaking. The circle and rect tags, which do not exist in HTML, do have a meaning in SVG. They draw shapes using a style and position specified by their attribute. These tags create DOM elements just like HTML tags that scripts can interact with. For example, this changes the circle element to be colored cyan instead. The canvas element. Canvas graphics can be drawn onto a canvas element. You can give such an element width and height attributes to determine its size in pixels. A new canvas is empty, meaning it is entirely transparent and thus shows up as empty space in the document. The canvas tag is intended to allow different styles of drawing. To get access to an actual drawing interface, we first need to create a context, an object whose method provides the drawing interface. These are currently three widely supported drawing styles: 2D for two-dimensional graphics, WebGL for three-dimensional graphics through the OpenGL interface, and WebGPU, a more modern and flexible alternative to WebGL. This book won't discuss WebGL or WebGPU. We'll stick to two dimensions. But if you're interested in three-dimensional graphics, I do encourage you to look into WebGPU. It provides a direct interface to graphics hardware and allows you to render even complicated scenes efficiently using JavaScript. You can create a context with the getContext method on the canvas DOM element. After creating the context object, the example draws a red rectangle that is 100 pixels wide and 500 pixels high with its upper left corner at coordinates 10, 10. Just like in HTML and SVG, the coordinate system that the canvas uses puts 0, 0 at the upper left corner, and the positive y-axis goes down from there. This means 10, 10 is 10 pixels below and to the right of the upper left corner. Lines and surfaces. In the canvas interface, a shape can be filled, meaning its area is given a certain color or pattern, or it can be stroked, which means that a line is drawn along its edge. SVG uses the same terminology. The fillRect method fills a rectangle. It takes the first x and y coordinates of the rectangle's upper left corner, then its width, then its height. A similar method called strokeRect draws the outline of the rectangle. Neither method takes any further parameters. The color of the fill, thickness of the stroke, and so on are not determined by an argument to the method, as you might reasonably expect, but rather by properties of the context object. The fill style property controls the way shapes are filled. It can be set to a string that specifies a color using the color notation used by CSS. The stroke style property works similarly but determines the color used for a stroked line. The width of that line is determined by the line width property, which may contain any positive number. When no width or height attribute is specified, as in the example, a canvas element gets a default width of 300 pixels and a height of 150 pixels. Paths. A path is a sequence of lines. The 2D canvas interface takes a peculiar approach to describing such a path. It is done entirely through side effects. Paths are not values that can be stored and passed around. Instead, if you want to do something with a path, you make a sequence of method calls to describe its shape. This example creates a path with a number of horizontal line segments and then strokes it using the stroke method. Each segment created with line 2 starts with the path's current position. That position is usually the end of the last segment unless move to was called. In that case, the next segment would start at the position passed to move to. When filling a path using the fill method, each shape is filled separately. A path can contain multiple shapes. Each move to notion starts a new one. But the path needs to be closed, meaning its start and end are in the same position before it can be filled. If the path is not already closed, a line is added from its start to its end and the shape enclosed by the completed path is filled. This example draws a filled triangle. Note that only 2 of the triangle's sides are explicitly drawn. The third from the lower right corner back to the top is implied and wouldn't be there if you stroked the path. You could also use the close path method to explicitly close a path by adding an actual line segment back to the path start. This segment is drawn when stroking the path. Curves. A path may also contain curved lines. These are unfortunately a bit more involved to draw. The quadratic curve to method draws a curve to a given point. To determine the curvature of the line, the method is given a control point as well as a destination point. Imagine this control point as attracting the line, giving it its curve. The line won't go through the control point, but its direction at the start and end points will be such that a straight line in that direction would point towards the control point. The following example illustrates this. We draw a quadratic curve from the left to the right with 60-10 as the control point, and then draw 2 line segments going through that control point and back to the start of the line. The result somewhat resembles a Star Trek insignia. You can see the effect of the control point. The lines leaving the lower corners start off in the direction of the control point and then curve towards their target. The Bezier curve to method draws a similar kind of curve. Instead of a single control point, this method has 2, one for each of the line's endpoints. Here is a similar sketch to illustrate the behavior of such a curve. The 2 control points specify the direction at both ends of the curve. The farther they are from their corresponding point, the more the curve will bulge in that direction. Such curves can be hard to work with. It's not always clear how to find the control points that provide the shape you're looking for. Sometimes you can compute them, and sometimes you just have to find a suitable value by trial and error. The arc method is a way to draw a line that curves around the edge of a circle. It takes a pair of coordinates for the arc's center, a radius, and then a start angle and an end angle. Those last 2 parameters make it possible to draw only part of a circle. The angles are measured in radians, not degrees. This means a full circle has an angle of 2 pi, or 2 times math.pi, which is about 6.28. The angle starts counting at the point to the right of the circle's center and goes clockwise from there. You can use a start of 0 and an end bigger than 2 pi, say 7, to draw a full circle. The resulting picture contains a line from the right of the full circle, first called arc, to the right of the quarter circle, second call. Like other path drawing methods, a line drawn with arc is connected to the previous path segment. You can call move to or start a new path to avoid this. Drawing a pie chart. Imagine you've taken a job at Econocorp, Inc. Your first assignment is to draw a pie chart of its customer satisfaction survey results. The results binding contains an array of objects that represent the survey responses. To draw a pie chart, we draw a number of pie slices, each made up of an arc and a pair of lines to the center of that arc. We can compute the angle taken up by each arc by dividing a full circle, 2 pi, or the total number of responses, and then multiplying that number, the angle per response, by the number of people who picked a given choice. But a chart that doesn't tell us what the slices mean isn't very helpful. We need a way to draw text onto the canvas. Text. A 2D canvas drawing context provides the methods fill text and stroke text. The latter can be useful for outlining letters, but usually fill text is what you need. It will fill the outline of the given text with the current fill style. You can specify the size, style, and font of the text with the font property. This example gives it a font size and family name. It is also possible to add italic or bold to the start of the string to select a style. The last two arguments to fill text and stroke text provide the position at which the font is drawn. By default, they indicate the position at the start of the text's alphabetic baseline, which is the line that letters stand on, not counting hanging parts of letters such as J or P. You can change the horizontal position by setting the text align property to end or center, and the vertical position by setting text baseline to top, middle, or bottom. We'll come back to our pie chart and the problem of labeling the slices in the exercises at the end of the chapter. Images. In computer graphics, a distinction is often made between vector graphics and bitmap graphics. The first is what we've been doing so far in this chapter, specifying a picture by giving a logical description of shapes. Bitmap graphics, on the other hand, don't specify actual shapes, but rather work with pixel data, rosters of colored dots. The draw image method allows us to draw pixel data onto a canvas. This pixel data can originate from an image element or from another canvas. The following example creates a detached image element and loads an image file onto it. But the method cannot immediately start drawing from this picture because the browser may not have loaded it yet. To deal with this, we register a load event handler to do the drawing after the image is loaded. By default, draw image will specify the image at its original size. You can also give it two additional arguments to specify the width and height of the drawn image, when those aren't the same as the origin image. When draw image is given 9 arguments, it can be used to draw only a fragment of an image. The second through fifth arguments indicate the rectangle x, y, width, and height in the source image that should be copied, and the 6th to 9th arguments give the rectangle on the canvas into which it should be copied. This can be used to pack multiple sprites, image elements, into a single image file and then draw only the part you need. For example, this picture contains a game character in multiple poses. By alternating which pose we draw, we can show an animation that looks like a walking character. To animate a picture on a canvas, the clear rect method is useful. It resembles fill rect, but instead of coloring the rectangle, it makes it transparent, moving the previously drawn pixels. We know that each sprite, each subpicture, is 24 pixels wide and 30 pixels high. The following code loads the image and then sets up an interval repeated timer to draw the next frame. The cycle binding tracks our position in the animation. For each frame, it is incremented and then clipped back to the 0 to 7 range by using the remainder operator. This binding is then used to compute the x-coordinate that the sprite for the current pose has in the picture. Transformation. What if we want our character to walk to the left instead of the right? We could draw another set of sprites, of course, but we could also instruct the canvas to draw the picture the other way around. Calling the scale method will cause anything drawn after it to be scaled. This method takes 2 parameters, one to set a horizontal scale and one to set a vertical scale. Scaling will cause everything about the drawn image, including the line width, to be stretched out or squeezed together as specified. Scaling by a negative amount will flip the picture around. The flipping happens around 0.00, which means it will also flip the direction of the coordinate system. When a horizontal scaling of -1 is applied, the shape drawn at x position 100 will end up at what used to be position -100. To turn a picture around, we can't simply add cx.scale -1 before the call to draw image. That would move our picture outside the canvas where it won't be visible. We could adjust the coordinates given to draw image to compensate for this by drawing the image at x position -50 instead of 0. Another solution, which doesn't require the code doing the drawing to know about the scale change, is to adjust the axis around which the scaling happens. There are several other methods besides scale that influence the coordinate system for a canvas. You can rotate subsequently drawn shapes with the rotate method, and move them with the translate method. The interesting and confusing thing is that these transformations stack, meaning that each one happens relative to the previous transformations. If we translate by 10 horizontal pixels twice, everything will be drawn 20 pixels to the right. If we first move the center of the coordinate system to 50-50 and then rotate by 20 degrees, about 0.1 pi radians, that rotation will happen around 0.50-50. But if we first rotate by 20 degrees and then translate by 50-50, the translation will happen in the rotated coordinate system and thus produce a different orientation. The order in which the transformations are applied matters. To flip a picture around the vertical line at a given x position, we can do the following. We move the y-axis to where we want our mirror to be, apply the mirroring, and finally move the y-axis back to its proper place in the mirrored universe. The following picture explains why this works. This shows the coordinate system before and after each mirroring across the central line. The triangles are numbered to illustrate each step. If we draw a triangle to position x at positive x position, it would by default be in the place where triangle 1 is. A call to flip horizontally first does a translation to the right, which gets us to triangle 2. Then it scales, flipping the triangle over position 3. This is not where it should be, if it were mirrored in the given line. The second translate call fixes this. It cancels the initial translation and makes triangle 4 appear exactly where it should. We can now draw a mirrored character at position 100, 0 by flipping the world around its character's vertical center. Storing and clearing transformations. Transformations stick around. Everything else we draw after drawing that mirrored character will also be mirrored. That might be inconvenient. It is possible to save the current transformation, do some drawing and transforming, and then restore the old transformation. This is usually the proper thing to do for a function that needs to be temporarily transformed the coordinate system. First, we save whatever transformation the code that called the function was using. Then the function does its thing, adding more transformations on top of the current transformation. Finally, we revert to the transformation we started with. The save and restore methods on the 2D canvas context do this transformation management. They conceptually keep a stack of transformation states. When you call save, the current state is pushed onto the stack, and when you call restore, the state on top of the stack is taken off and used as the context's current transformation. You can also call reset transformation to fully reset the transformation. The branch function in the following example illustrates what you can do with a function that changes the transformation, and then calls a function, in this case itself, which continues drawing with the given transformation. This function keeps a tree-like shape by drawing a line, moving the center of the coordinate system to the end of the line, and calling itself twice, first rotated to the left and then rotated to the right. Every call reduces the length of the branch drawn, and the recursive stops when the length drops below 8. If the call to save and restore were not there, the second recursive call to branch would end up with the position and rotation created by the first call. It would be connected not to the current branch, but rather to the innermost rightmost branch drawn by the first call. The resulting shape might also be interesting, but is definitely not a tree. Back to the game. We now know enough about canvas drawing to start working on a canvas-based display system for the game from the previous chapter. The new display will no longer be showing just color boxes. Instead, we'll use draw image to draw pictures that represent the game's elements. We define another display object called canvas display, supporting the game interface as DOM display from chapter 16, namely the methods syncState and clear. This object keeps a little more information than DOM display. Rather than using the scroll position of its DOM element, it tracks its own viewport, which tells us which part of the level we are currently looking at. Finally, it keeps a flip player property so that even when the player is standing still, it keeps facing the direction in which it last moved. The syncState method first computes a new viewport and then draws the game scene at the appropriate position. Contrary to DOM display, this display style does have to redraw the background on every update. Because shapes on a canvas are just pixels, after we draw them, there's no good way to move them or remove them. The only way to update the canvas display is to clear it and redraw the scene. We may also have scrolled, which requires the background to be in a different position. The update viewport method is similar to DOM display's scroll player into view method. It checks whether the player is too close to the edge of the screen and moves the viewport when this is the case. The calls to math.max and math.min ensure that the viewport does not end up showing space outside the level. Math.max x 0 makes sure the resulting number is not less than 0. Math.min similarly guarantees that a value stays below a given bound. When clearing the display, we'll use a slightly different color depending upon whether the game is won, brighter, or lost, darker. To draw the background, we run through the tiles that are visible in the current viewport using the same trick used in the touches method from the previous chapter. Tiles that are not empty are drawn with draw image. The other sprite's image contains the pictures used for elements other than the player. It contains from left to right the wall tile, the lava tile, and the sprite for a coin. Background tiles are 20 by 20 pixels, since we'll use the same scale as in DOM display. Thus the offset for lava tiles is 20, the value of the scale binding, and the offset for walls is 0. We don't bother waiting for the sprite image to load. Calling draw image with an image that hasn't loaded yet will simply do nothing. Thus we might fail to draw the game properly for the first few frames while the image is still loading. But that isn't a serious problem. Since we keep updating the screen, the correct scene will appear as soon as the loading finishes. The walking character shown earlier will be used to represent the player. The code that draws it needs to pick the right sprite and direction based on the player's current motion. The first 8 sprites contain a walking animation. When the player is moving along the floor, we cycle through them based on the current time. We want to switch frames every 60 milliseconds, so the time is divided by 60 first. When the player is standing still, we draw the 9th sprite. During jumps, which are recognized by the fact that the vertical speed is not 0, we use a 10th rightmost sprite. Because the sprites are slightly wider than the player object, 24 instead of 16 pixels to allow some space for feet and arms, the method has to adjust the x coordinate and width by a given amount, player x overlap. The draw player method is called by draw actors, which is responsible for drawing all the actors of the game. When drawing something that is not the player, we look at its type to find the offset of the correct sprite. The lava tile is found at offset 20, and the coin sprite is found at 40, 2 times scale. We have to subtract the viewport's position when computing the actor's position, since 0, 0 on our canvas corresponds to the top left of the viewport, not to the top left of the level. We could also have used translate for this. Either way works. This document plugs the new display into Run Game. Choosing a graphics interface. When you need to generate graphics in the browser, you can choose between plain HTML, SVG, and Canvas. There's no single best approach that works in all situations. Each object has its strengths and weaknesses. Plain HTML has the advantage of being simple. It also integrates well with text. Both SVG and Canvas allow you to draw text, but they won't help you position that text or wrap it when it takes up more than one line. In an HTML-based picture, it is much easier to include blocks of text. SVG can be used to produce crisp graphics that look good at any zoom level. Unlike HTML, it's designed for drawing and thus more suitable for that purpose. Both SVG and HTML build up a data structure, the DOM, that represents your picture. This makes it possible to modify elements after they are drawn. If you need to repeatedly change a small part of a big picture in response to what the user is doing, or as part of an animation, doing it in a canvas can be needlessly expensive. The DOM also allows us to register mouse event handlers on every element in the picture, even on shapes drawn with SVG. You can't do that with Canvas. But the Canvas's pixel-oriented approach can be an advantage when drawing a huge number of tiny elements. The fact that it does not build up a data structure, but only repeatedly draws onto the same pixel surface, gives Canvas a lower cost per shape. There are also effects that are only practical with a Canvas element, such as rendering a scene 1 pixel at a time, for example using a ray tracer, or post-processing an image with JavaScript, blurring or distorting it. In some cases, you may want to combine several of these techniques. For example, you might draw a graph with SVG or Canvas but show textual information by positioning an HTML element on top of the picture. For non-demanding applications, it really doesn't matter which interface you choose. The display we built for our game in this chapter could have been implemented using any of the 3 graphics technologies, since it does not need to draw text, handle mouse interaction, or work with an extraordinarily large number of elements. Summary. In this chapter, we discussed techniques for drawing graphics in the browser, focusing on the Canvas element. A Canvas node represents an area in a document that our program may draw on. This drawing is done through a drawing context object created with the getContext method. The 2D drawing interface allows us to fill and stroke various shapes. The context fill style property determines how shapes are filled. The stroke style and line width properties control the way lines are drawn. Rectangles and pieces of text can be drawn with a single method call. The fill rect and stroked rect methods draw rectangles, and the fill text and stroke text methods draw text. To create custom shapes, we must first build up a path. Calling begin path starts a new path. A number of other methods add lines and curves to the current path. For example, line 2 can add a straight line. When a path is finished, it can be filled with a fill method or stroked with the stroke method. Moving pixels from an image or another canvas onto our canvas is done with the draw image method. By default, this method draws the whole source image, but by giving it more parameters, you can copy a specific area of the image. We use this for our game by copying individual poses of the game character out of an image that contain many such poses. Transformations allow you to draw a shape in multiple orientations. A 2D drawing context has a current transformation that can be changed with the translate, scale, and rotate methods. These will affect all subsequent drawing operations. A transformation state can be saved with the save method and restored with the restore method. When showing an animation on canvas, the clear rect method can be used to clear part of the canvas before redrawing it. Exercises. Shapes. Write a program that draws the following shapes on a canvas: a trapezoid, a rectangle that is wider on one side, a red diamond, a rectangle rotated 45 degrees or 1/4 pi radians, a zigzagging line, a spiral made up of 100 straight line segments, a yellow star. When drawing the last two shapes, you will want to refer to the explanation of math.cosine and math.sine in Chapter 14, which describes how to get coordinates on a circle using these functions. I recommend creating a function for each shape, pass the position, and optionally other properties such as the size or number of points as parameters. The alternative, which is to hardcode numbers all over your code, tends to make the code needlessly hard to read and modify. The pie chart. Earlier in the chapter, we saw an example program that drew a pie chart. Modify this program so the name of each category is shown next to the slice that represents it. Try and find a pleasing way to automatically position this text that would work for other datasets as well. You may assume that categories are big enough to leave enough room for their labels. You might need math.sine and math.cosine again, which are described in Chapter 14. A bouncing ball. Use the request animation frame technique we saw in Chapter 14 and 16 to draw a box with a bouncing ball in it. The ball moves at a constant speed and bounces off the box's sides when it hits them. Pre-computing mirroring. One unfortunate thing about transformations is they slow down the drawing of bitmaps. The position and size of each pixel have to be transformed, and though it is possible that browsers will get clever about transformation in the future, they currently cause a measurable increase in the time it takes to draw a bitmap. In a game like ours, where we're drawing only a single transformed sprite, this is a non-issue, but imagine that we need to draw hundreds of characters or thousands of rotating particles from an explosion. Think of a way to draw an inverted character without loading additional image files, and without having to make transform draw image calls every frame.